Okay, so we left off last week at this expression up here with the delta G equals RT logarithm K, and of course that must be the same as delta H minus T delta S. Now, in the last lecture, we had derived that the logarithm of the equilibrium constant must correspond to this left-hand expression, where you have as the first term the difference in the potential energy, so at 0 Kelvin over RT due to that chemical reaction. So again, you can have a figure like this, right? So if this is your product and the reactant, then for T, so we can look at the energy, and this would be our delta E0. And so this corresponds to the enthalpic effect as we had discussed last week, right? So it's the enthalpy. And the second term, the more interesting one, is the one that contains the partition functions raised to the stoichiometric factor nu of products over reactants. Okay, and this you can directly relate to the entropy. We then went ahead and we discussed multiple examples of this interpretation. In particular, we discussed spectra of reactant and products that look like that. Something that looks like that. And I would now like to still bring a last example where not the spectrum plays the main role, or we don't look at the spectrum, but rather at these stoichiometric factors. So let's consider as an example the stoichiometry. In particular, consider a system of two components, A and B, that's in equilibrium with A and B. In that case, you would have to take the product of the two partition functions of the individual parts. And it stands to argue that that will always be larger 1 because you have all these degrees of freedom, and so you get a much larger number, right? Even though maybe AB has more states, still the product of QA and QB will win. And so that means that our delta S will be much larger 0, right? So the stoichiometry really can drive your reaction. And you know this already, right? So this shouldn't come as a surprise. But now you have seen where it comes from, right? So you should know this already as Chatelier's principle. All right, where we can shift the equilibrium with an external variable. So for example, if I wish to operate in the other direction, I would like to create the reactant AB. Right? I'd like to shift the equilibrium towards the reactant. I can accomplish that by simply increasing the concentration of B, or also simply increasing the pressure, and that will have the effect that the concentration of AB will grow. An example for such a system could be the Haber-Bosch procedure, where we would like to create ammonia from N2 and H2. Now, ammonia is a very precious starting material for fertilizers and chemical industry. So that's highly valuable. Molecular nitrogen is abundant in our atmosphere, and H2 is precious. Right? So the thing to do is to simply increase the N2 concentration, which is akin to increasing the pressure of the Earth's atmosphere, or the air in which you operate this. Right? And so that will consume then each and every little mole of H2. So doing this will minimize H2 consumption and maximize NH3 yield. Okay. Now, there's no free lunch. You have to pay in terms of energy you need to provide in order to increase the pressure. Right? So the ultimate currency in chemistry and elsewhere is energy. And so that's how you can do that. Now, this is just an example. These theories, right, are general, right? So particular, this expression here, right? And so no matter what reaction you're studying, you can consider this and then ask yourself, what is the structure of the reaction equation, and how do I shift it in the desired direction? Are there questions on this part? You can also write the questions in the chat if you prefer. Okay, I don't see any questions. So let's move ahead, and I'd like to, with this example, to conclude this course. Right, so we reached the end, and I'd like to recapitulate a little bit what we have done. So first we had the introduction, where we refreshened a little bit your classical thermodynamics. And I hope I could convince you that nothing of what we have discussed in this course was in conflict with thermodynamics. It basically deepened your understanding of it in terms of a microscopic picture, right? And this microscopic picture was what we discussed. After the thermodynamics, we then proceeded to discuss the partition function and in particular we started out by introducing the notion of the ensemble. Right? This was a theoretical exercise, but it laid the conceptual foundation, which enabled us to then proceed and to follow Boltzmann and his probability. In chapter 3, we then discussed how the most common state functions look like if we go via Boltzmann's probabilities and the statistical expectation values. So we discussed the energy, pressure, the work and heat, and finally the entropy. So these first 3 chapters were very fundamental and theoretical in nature. And they were also exact, okay? Without any approximations. And we then went ahead and introduced some approximations which make the theory more applicable, right? So this is always a there's always pros and cons with that, right? You lose through the approximations, you lose the accuracy and the full understanding of the problem, but in exchange you obtain you find a way to make to gain insights that are more useful to real life. So that's what we discussed in chapter 4 with the degrees of freedom, and in particular the modes of energy, where we factored out the partition function, and then we discussed the individual modes, that is the translational, the rotational, the vibrational, and the electronic partition functions. And then is the last chapter. We discussed the application and interpretation of these partition functions in the context of the equilibrium constant and the free energy of reaction. So we have 5.1. There was an introduction to this. Discussed reactions. Link Q. And some examples. All right. Are there any question on the material of this course, which we now reviewed? Doesn't seem to be the case. All right. So I'd still like to remark on the exam next week that this exam will cover what everything we dealt with in this course, and it is an open book exam, and I'm trying to limit the questions really to topics that we also discussed in class. So if you took your notes, if you attended class, you shouldn't have any problem in passing the exam. The tutorials and homework also prepared you for the exam. So if you want to study for the exam, in addition to revising your notes from the lectures, and of course you can also make use of the YouTube recordings, I would recommend also to revise the homework and quizzes which you did with a tutor. Okay, there's a question. Open book means that you can bring any notes you wish. So you can bring books, your handwritten notes, whatever. And there's a second good point. You may not bring electronic devices because this is, of course, dangerous for cheating. So I would not bring electronic notes to the exam, just paper and books. Are there any further questions? Can we print any resources we find out online and bring to the exam? Yes, you can. You can print whatever you find. Yeah. Okay. So again, I'm sorry I couldn't make it in person on our last day. I hope you did enjoy this course. And I wish you good luck for the exam and good studying. And also, independently of that, I would like to wish you a good continuation of your studies.
Thank you, Professor.
Thank you. I'm seeing a question by Mahmoud Al-Hamed that you have not been asked your question. I believe I asked all students, but I'm happy to check this real quick. If you don't mind, you can stay online. Okay. Mahmoud Alhamed, I will send you an email separately. Okay.
Okay, thank you, Professor.
No problem. And then I was still hoping for Halifa Wong, if you don't mind staying.